Welcome back. Today's topic, as you can see, is gravitational force and orbits. So to start us off, I'm going to bring us back to 1665, when Isaac Newton, who you've probably heard about, was a 22-year-old kid, basically. He was in college when the bubonic plague hit London, and they asked everyone to socially distance and stay home if they could. And Newton was a very rich kid, so he had a family estate out in the fields outside of London, and he stayed there for a whole year while the pandemic subsided. During that time, he came up with his best ideas, including the situation that he's best known for, which is when he was underneath a tree reading, and suddenly an apple fell, and it got him thinking, why does stuff fall to the earth? And Newton determined that there had to be a force that the Earth exerted on objects that attracted those objects to the Earth. And he called that gravitational force. Until there, we all know this. But he went a step ahead and he said, not only does the Earth attract objects, but every single object that has a mass attracts any other object. So that's important enough to write it down. So basically, gravitational force can be described as the force of attraction between any two objects that have mass. The only thing that an object has to have in order to be attracted to others and attract others is mass. So if you've ever wondered if you're attractive, Newton tells you that you are. Right now, every one of us is attracting every single object. And we're attracting the Earth even. So due to Newton's third law of motion, the force of attraction that the Earth does on us is exactly the same as the force of attraction that we exert on the Earth. But we accelerate at 9.8 meters per second squared towards the Earth, while the Earth doesn't, we can't really see it accelerate towards us. So that happens because even though the forces are the same, maybe 600 newtons is the force for both, the masses are completely different. So a force of 600 newtons on me has the effect of an acceleration of 9.8. The force of 600 newtons on the whole planet has an acceleration of maybe 0.0001. So that's why we don't notice it, but we are constantly attracting the Earth. And Newton took this even further. He gave another step. What his genius idea is that he connected the 2 points. He said, the same force that makes apples fall down to the ground is the force that is keeping the moon revolving and orbiting around the Earth, and the Earth orbiting around the sun. And he was right. He was the first person to say this, but basically, gravitational force is acting as the centripetal force that is keeping all celestial bodies in orbit around each other. So that's really important. Gravitational force acts as centripetal force to keep all celestial bodies in orbit. And because Newton was a very good mathematician, he decided to express this as a law, as an equation. So he called that Newton's law of universal gravitation. What Newton determined is that the gravitational force depended on 2 things. There have to be 2 objects, each one of them has to have a mass, so the equation has to talk about 2 different masses, and these objects are at a distance from each other. The farther away they are from each other, the less gravity they exert on each other. And the closer they are, the more gravity. So the force of gravity has to be proportional to the masses and inversely proportional to the distance between those masses. So he wrote it like this. This G is called the gravitational constant, and it's a number. More specifically, G is equal to 6.67 times 10 to the negative 11 meter cubed per kilogram times second squared. These are the units of the gravitational constant. These 2 are masses, so M1 and M2 are masses in kilograms. And R is the distance between the 2 objects in meters. It's important to recognize here that there's a squared in the r, and that makes this equation part of a group of equations called inverse square laws. Inverse because it's at the bottom, and square because it has a squared. You're going to come up to other inverse square laws in physics, specifically in electromagnetism. If you're talking about a planet specifically, such as the Earth, as we usually are, then one of these masses is going to be the mass of the Earth. And what would be the distance? So we take as the distance the radius of the Earth, because if the Earth is here and we're standing on top of the Earth, at the surface of the Earth, the distance between the center of mass of the Earth, which is at its center, and our center of mass is basically the radius of the Earth, plus a little bit more from our height, but that really means nothing when you compare it to the millions of kilometers of the radius of the Earth. So specifically for Earth, we can change this equation and put in the values for the mass of the Earth and the radius of the Earth, such that it looks like this. So for Earth specifically, we end up with this equation. So G is the same gravitational constant. It's the same for the whole universe. That never changes. ME is the mass of Earth, which is 6 times 10 to the 24 kilograms. And RE is the radius of the Earth, which is 6.4 times 10 to the 6 meters. So 6.4 million meters. So you put in those values and you put your mass here, or the mass of the object that you want to determine, and it's going to give you the force of gravity on Earth. But you might remember here and say, wait, we had already figured out the force of gravity on Earth, and we had determined the acceleration of gravity on Earth. So how is this related? How come we have two different equations? Well, it turns out they're not different equations. We simply get the things that are constant for Earth, in this case, G, mass of Earth, and radius of Earth, and we put this into its own constant that we call lowercase g. And as you know very well, lowercase g is an acceleration, and it has a value of 9.8 meters per second squared. So this is where 9.8 came from the mass of the Earth and the radius of the Earth. So if you multiply m times g, you get the force of gravity, as we had learned in previous classes. If you were to change this to figure out the force of gravity on the moon, for example, so you put the mass of the moon and the radius of the moon, you're going to get that these three values give a g of 1.6 meters per second squared, the acceleration of gravity on the moon. But coming back to Newton's law of universal gravitation, remember that we said that this force of gravity is acting as centripetal force. And we had an equation for centripetal force, which was mv squared over r. So you can equal these two, mv squared over r and g m1 m2 over r squared, and that'll give you information about the speed that you need for a certain orbit. So we're not going to actually do the math, but I'm going to tell you a couple of results of doing that math. So one of the results is called orbital velocity. You know, the Earth is round, and suppose you are here on Earth and you throw a ball really, really hard. So hard that you can actually see its trajectory from outer space, and it falls many kilometers ahead. If you throw it a little harder, it's going to reach even more. And if you throw it harder, even more. So, as you might assume, there's a point at which, when you throw it, it never reaches the Earth. It just enters an orbit, and it continues in that orbit forever. So the speed that you need to put any object in orbit is called the orbital velocity. In the case of Earth, that orbital velocity is between 6.9 and 7.8 kilometers per second. So it's a really, really fast speed that you need to achieve in order to put something in orbit. That's the way that engineers and physicists put satellites in orbit. They throw them out at a speed in these ranges so that they enter the orbit of the Earth. Every 1.5 to 2 hours, something thrown with this speed will give a complete revolution around the Earth. But what happens if you throw it even harder? What if it didn't enter an orbit, but you throw it so hard that it doesn't even enter the gravity of the Earth. So that's what we call escape velocity. So escape velocity is actually that, the speed that you need to give an object when you throw it so that it goes out of the Earth's gravitational pull and never returns. It ends up going straight in space forever and you will never see it again. In Earth, that speed is 11.2 kilometers per second. If we weren't on Earth, but on a planet that had more gravity, maybe because it has more mass, or because it has a smaller radius with the same mass, you would need a higher escape velocity to escape its gravitational pull and a higher orbital speed to enter its orbit. So the more massive, the more speed you need. The less radius, the more speed you need.